Welcome back, everyone. I hope that you enjoyed experimenting with our applet there. So we were trying to figure out what f being concave up told us about f prime and vice versa. So I've filled in a few tangent lines here. So an f prime here maybe would be, say, -2, -1, 0, 1, and 2. So we certainly can't say that if f is concave up, f prime is always positive or always negative. But I hope the word that you did fill in was the word increasing. So that is going to be our definition of f being concave up, is where f prime is increasing. So even though these slopes are getting shallower at the start, why is f prime technically increasing here at the start? That's because f prime is going from a negative number to a less negative number. -2, -1, 0, 1, 2, those numbers are increasing when we read them left to right. If the temperature goes from -2 to -1 to 0 to 1 to 2, the temperature is increasing the whole time. And this is a point to mention that we always read graphs from left to right. In fact, I am reliably assured that even in languages where the text is written from right to left in a book, if a graph appears embedded in the text, you still read the graph from left to right. So we're always going to read graphs from left to right. Similarly, if f is concave down, I guess I didn't leave myself enough room to write the answer here. F prime is, so what are the slopes doing here? First they're getting shallower, then they're getting steeper, but what are the slopes doing the whole time? I hope the word that you came up with was decreasing. So if f is concave down, if f prime is decreasing, because we're going from a big positive to a lesser positive to a small negative and then to a bigger negative. So f is concave down when f prime is decreasing. So that means we can fill in two of our boxes over here. F is concave up just by our definition when f prime is increasing. F is concave down by our definition when f prime is decreasing. Now, what did you put in for the other boxes? F being positive simply tells us that the graph of f is above the x-axis. We have no other information about f. F could be going upward, could be going downward, could be horizontal. So just knowing, for example, that the temperature is positive tells us nothing about the rate of change of the temperature. So this is one of the ones that, as promised, gets an x. F positive tells us nothing about its slope. F negative just means that the graph is below the x-axis. So if the temperature is negative, do you know if the temperature is going up or going down? You have no idea. Just could be a cold day that's getting colder or a cold day that's getting warmer. So there's no relationship there. On the other hand, if a function is increasing, then what do you know about its slope? The graph is going upward. It must have a positive slope. If a function is decreasing, that means the graph is going downward. It must have a negative slope. So this is a chart that's going to be useful for us. And in fact, by the end of the week, we will be able to add a third line underneath this for f double prime, another how it relates to both of these. So we're going to copy this chart onto the next chalkboard. So here's a small version of the chart. I've just abbreviated some of the words. And now we want to try, as promised, given a graph of f, we want to sketch what f prime looks like. And we'll try to take use of the chart where it's appropriate. So here's my first graph of f. F is simply a perfectly horizontal line. A lot of people like to call these straight lines, but really all lines are straight. This is a horizontal line. And we want to draw f prime, which, remember, is the slope of f. So let's start here. What's the slope of f right here? If you said 0, you're right. What's the slope of f right here? Again, 0. Slope of f here, 0. Slope of f here, 0, 0, 0. So no matter what x value I pick, f prime is always 0. So how will I show that down here? That's just going to be somehow trying to shade in the x-axis a little bit to show that f prime is always 0. Because my graph of f is a horizontal line. F is not changing. If the temperature were just staying the same the whole time, then the rate of change would just always be 0. So the chart wasn't really too useful for that one. How about this one here? Now I've got an f that's linear, and f is going downward. So what do we know about the slope of f? If you might say that the slope of f is, say, -1 here, then because this is a linear function, the slope of f should be what here? still negative 1, still negative 1, still negative 1. So I want to draw a graph of f prime whose y values are always negative 1. That's going to be a horizontal line down below the x-axis. Now, one thing I could have mentioned back here, I should have, is what if we had just taken this graph and shifted it down here below, like that, for f? Would that have changed f prime? I hope you would agree with me that it would not. When I take this graph and I shift it up or down, all I'm changing is whether f itself is maybe positive or negative, but that doesn't affect f prime at all, right? If I take the graph and I shift it up or down, like if I take this graph and I shift it down, will f prime change at all? And I hope you agree that the answer is no. So in particular, this point here where my first graph of f was crossing the x-axis is completely irrelevant when I'm sketching f prime. So do not be distracted by where f crosses the x-axis when you're sketching f prime. So if we want to think about this in terms of our chart here, what do we know about f? F is decreasing. So f prime should be negative, which is what we drew. F prime was below the x-axis. But our graph of f, being a line, was neither concave up nor concave down, meaning f prime was neither increasing nor decreasing. And if you're neither increasing nor decreasing, you really only have one other option, and that's to be constant, straight, horizontal line. Like that. Let's move on to a more interesting one here. What I find to be useful for these is to start off by identifying the places where I know the slope of f exactly. And that's going to be where the slope of f is 0. So ask yourself, and for all of these, I think it's a good thing to pause the tape and try to draw your f prime yourself. But how many places do you see where f prime is 0 here? I see 2. I've got f prime is not 0. Now f prime is 0. So if I draw straight down from there, I know that my graph of f prime is going to have to touch the x-axis at that point. And then I think it's going to happen one more time out here. Right? Again, I have a perfectly horizontal tangent line. So if I were to drop straight down from there, my f prime should touch the x-axis there. And nowhere else. So these are the only places where f prime is going to touch the x-axis. So let's start out over here. We've got a slope of f that is what? The slope of f is negative. And the slope of f as I go along is getting less negative. That means that f prime is a negative number, in other words, below the x-axis, but getting less negative, meaning coming upward. Now, I'm intentionally drawing this a little wavy. We'll talk about why in a minute. If I wanted to do this from the chart, what two things did I know about f that were important here? Remember, f being positive and negative is not important, so don't worry about that. We know that f is decreasing and f is concave up. So if you go back to your chart here, you chose that f was decreasing and concave up. I hope you chose that. So what does that mean about f prime? F prime should be negative and f prime should be increasing, which is in fact exactly what we drew here. F prime was negative, meaning below the x-axis, increasing, meaning going upward. Let's keep going now. Now what's happening to the slopes? Now the slopes are positive and they're becoming more positive. So we've got a positive slope going up and up and up. And then eventually the slopes start to level off and become less positive. Coming down like that. So if, for example, we wanted to do this first part from about here to here using our chart, what two things do we know about f? F is increasing, going upward, and f is concave up. So if you choose that f was increasing and f was concave up, what two things does that tell us about f prime? F prime should be positive and increasing, which is exactly what you drew there. And then finally now, for a while, the slopes are getting more negative. So we're coming down and down. But what's happening to the slopes over here as we go along? This graph is becoming closer and closer to a horizontal line. So the slopes are leveling off, coming up towards some kind of horizontal asymptote there. So even though this was a horizontal asymptote at, let's say, x equals 3, or y equals 3, this horizontal asymptote is going to be at y equals where? Y equals 0, because these slopes are getting closer and closer to 0. Now, why did I not draw this in a way that was concave down or concave up? You'll notice that in our chart, in our line for f prime, the words concave up and concave down never appear at all. If we could somehow put 2 more columns out here, then we could write the words concave up and concave down. But the way that our brains work, or the way that our eyes see, doesn't allow us to do that. For example, if this piece here had been a perfect parabola, right? I could have taken a perfect parabola and stitched it together with some other curve out here. We learned last week that when we took the derivative of a parabola, we got a linear function. So if this is a parabola, then the f prime is actually perfectly linear down here. But can you tell me for certain that this is or is not a piece of a perfect parabola? I don't think you can. I can't. Just from a picture, if we don't have a formula, there's no way to tell. So if this were a perfect parabola, this would be a line. If this were slightly more bent than a parabola, this would be concave one way and slightly less concave the other way. So as long as you get the features of f prime being positive and negative and increasing and decreasing right, that's all we can say. Nobody can tell you you're wrong. So if you had drawn this as a line here, or if you had drawn it as concave down, or if you had drawn it as concave up, those are all possibly correct answers. There's no way to tell just from the graph whether graph of f, whether f prime should be concave up or concave down. All right, let's go to this one. So again, if we adopt that same strategy, we should identify places where the derivative is 0. So there's one right there. And I think that's the only one. So this starting part of the graph, the slope is negative, getting less negative. So that's similar to what we had over here. So somehow like that. And again, we don't know the concavity. And now what happens when we go up like this? So the question, the interesting question is, f has a vertical asymptote. Will f prime have a vertical asymptote or not? So think to yourself for a second here. If f has a vertical asymptote, is f prime guaranteed to have a vertical asymptote, or might f prime not? If f prime did not have a vertical asymptote, that would mean that somehow f was going up and up and up like this, and then eventually got to some highest point. So let's say this highest point is even 1,000. That means that f prime never gets more than 1,000, meaning the slope of f never gets more than 1,000. But what would that mean? That would mean that this graph is going up and up and up, and eventually it reaches some point beyond which its slope cannot exceed 1,000, meaning it's going to have to stay at a slope of 1,000, but then what's it going to do? The graph of f would have to hit that vertical asymptote. But vertical asymptotes are the ones that we don't hit. We cannot cross a vertical asymptote. We can cross a horizontal asymptote, right? I crossed this one right here. But I cannot cross a vertical asymptote. So we know that it's not the case that f eventually levels off at a slope of 1,000. That can't happen. It couldn't happen at a slope of 1,000,000 or 1,000,000,000. So this cannot happen. What must happen instead is that f prime must also have a vertical asymptote going up and up and up forever. There's no other possibility. If f has a vertical asymptote, f prime has to have a vertical asymptote as well. Similarly, on the other side, what kind of slope do I have now? We have some huge negative slope, meaning that f prime is coming from down here on the other side of the vertical asymptote. And what's happening to our slope? It's negative and getting less negative as we go. So I've got something coming like this. But we also have a vertical asymptote there. So one important thing to remember is that if we have a horizontal asymptote on f, f prime will also have a horizontal asymptote, but the horizontal asymptote on f prime will always be at y equals 0. If I have a vertical asymptote on f, f prime has to have a vertical asymptote at exactly the same x value. Let's look at one more graph here. So this very simple looking graph is the absolute value function. And let's try to figure out what the graph of its derivative looks like. So we're saying the slope here is just -1, -1, -1, -1. So I'm coming along happily here at a y value of -1. I'm not sure what happens when I get to this corner point. And here I'm coming happily along at a slope of what? 1, 1, 1, 1, 1. So here we're going at a horizontal line at 1. And the question is, what should we say about the slope at 0? What do you think it should be? Should it be 0? Should it be 1? Should it be -1? Should it be 1 and -1? Should it be none of the above? Cast your vote. Let's see if we can figure it out using our limit definition. So this is the definition of an absolute value function. Your x, if you're not negative, you're negative x if you are negative. We're interested in figuring out the slope at 0. So we use our limit definition to plug for the slope at 0, f of 0 plus h minus f of 0. But f of 0 plus h, of course, is just the same as saying f of h. And what is f of 0 for our absolute value function? It's 0. So really what we're doing is we're computing the limit as h goes to 0 of f of h over h. But as we have said multiple times, when we say h is going to 0, we don't know whether h is coming from the right or from the left. And we have to get the same answer from both sides. So we would have to get the same answer for the slope from this side as the slope from this side. So from the graph, you should ask yourself now, do you think that's true? When h is approaching 0 from the right, is the slope here the same as when h is approaching 0 from the left? If you think it is, then whatever that slope is, that one single number, that's what we should put for f prime of 0. If you think that it's a different slope from the left and the right, then you should say that the derivative is undefined at that point because the limit doesn't exist. The limit is different from the left and the right. So let's figure it out here. When h is approaching 0 from the right, we're trying to compute this limit and see if it's the same from the right and from the left. If h is greater than 0, that means we're in this part of the graph of f, of this piecewise function here. So f of h is just h. But what is h over h? That's just 1. So that's probably what you expected, right? I've got a slope of 1, 1, 1, 1, 1 as I'm coming towards 0 from the right. When we're coming from the left, that means we're in this part of the piecewise function. H is less than 0. So f of h is minus h. But minus h over h is negative 1. And again, that's what I hope you had guessed from this graph here, right? I've got a slope of negative 1, negative 1, negative 1. And since I got a different limit from the right than from the left, going back to week 2, what do we say about the limit? We say thus the limit as h goes to just 0 of f of h over h does not exist. Meaning that f prime of 0 does not exist. So now we have to show that in this graph here by putting an open dot. Sometimes people call these open circles, but technically all circles are open. If you fill in a circle, you have what's called a disk. But these are circles. These are open dots. So this shows that at x equals 0, there is no y value, right? I don't have a y value of 1. I don't have a y value of negative 1. So this function's derivative does not exist at x equals 0. And this leads us to a new word. If the derivative does exist at a certain point, then we say the function is differentiable at x equals c at that point. If the derivative, so in this case, the absolute value function is not differentiable at 0. But it is differentiable everywhere else, right? I know what the slope is at all of these other points. And we should have one more definition that goes along with our concave up, concave down that we started off the week with. A point at which f of x changes from concave up to concave down or vice versa. This is given a special name, from concave up to concave down or concave down to concave up. And this is another one of those words that has escaped from math and is being misused out in the general public is called an inflection point. That's where we change from concave up to concave down. So let's try to draw a graph and see how many inflection points it has. So suppose this is my graph of f. How many inflection points does this graph have? Remember, it's a place where we change from concave up to concave down. So often I will hear somebody on the news saying, for example, oh, the stock market is at an inflection point, or the housing market is at an inflection point. And it's clear from the context that they are meaning it is either at a low point or a high point, and they are just trying to use a fancy word. We already have a word for high point. It's called maximum, and we have a word for low point. It's called minimum. Inflection point is something else. So in this case, we're concave what at the start? We're concave up, 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 up. And then maybe somewhere around here, we change to concave down, right? And now we're concave down, 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 down. And maybe somewhere around here, we change to concave up. So this graph, if you chose it correctly, has 2 inflection points. So let's use the word inflection point correctly in this class. This point is called the minimum. This is a minimum. This is a maximum. That's not what we're talking about when we mean inflection point. Place where we change between concave up and concave down. That is what we mean by an inflection point. And now we have a check your understanding for you about sketching graphs of derivatives.